So I was trying to think of some ways to deliver to you these ideas that I've kind of had about how to express creativity in the form that it takes within mathematics. And a few quotes came to mind. One of them was the quote from Plato's Republic that said, "Our need will be the real creator." And from that it got changed over time to become, "Necessity is the mother of invention." Maybe mistranslated or modulated or however you want to say it. Over time this became associated with Plato, even though his original quote translated properly into English would be something along these lines. Another quote comes from Agatha Christie, a famous author, and she said, "I don't think necessity is the mother of invention. Invention, in my opinion, arises directly from idleness, possibly also from laziness, to save oneself trouble." And I don't know. I think all of us have this kind of laziness inside. In fact, I got really good at mental calculation, and by extension, I got better at paper calculation because I was good at the mental calculation, because I didn't want to get up and get a pencil. Like, I was laying down in bed before, we didn't have phones back then, and you're holding a piece of paper looking at an old SAT test perhaps, and my pencil's over there, and I'm over here, you see, and I'm relaxed and I'm comfortable. I would have to get up and go over there to actually grab the pencil and then solve it, and I don't want to do that. I'm comfortable. So I actually got to a point where I could solve the older SAT test, not the current ones, but pre-2015. The older SATs were actually more like a easier AMC 8, perhaps. There was a lot of creative problem solving in them. The modern versions of them are pretty terrible and not much fun to do, but I could do the old SAT in about half the time as most people would do it regular, and I would get everything right. And that's my practice for doing that, because you'd have to hold these ideas in your mind, and at first it's kind of difficult, and I'll demonstrate maybe later, either in this video or another, an example of me doing that. You might see a couple where I did mental calculation of things. But I wanted to get to this idea, and I'm not so sure that these are different. See, one will say that laziness, various people have now said that laziness is the father of invention. I found at least, a few dozen people, or half a dozen, whatever, I don't know, quite a few people claiming the title that laziness is the father of invention. And of course, necessity, laziness, mother, all that kind of stuff ties together. But are they really that different of quotes? If you think about it, it depends on how great your need is to be lazy, right? There's a famous quote too from somebody you might have heard from, Ben Franklin. The inventor once said that he is the laziest man in the world. I invented all those things to save myself from toil. A lot like what C's saying here, Agatha Christie, to save oneself trouble. And so I wanted to give an example of this. I kind of had this, I did this in high school actually. Maybe some of you have come up with the same thing, and perhaps it's not that great of a deal, but I'd like to show you an example of what that looks like. If we look at graphing, y equals, right, 3/4 x plus 1, okay? And this is mx plus b, and everybody knows how this goes, and you go to 1 on the y-axis, and you go, there's my y-intercept, you have rise over run, 1, 2, 3, and then you're going to go over 4. 1, 2, 3, 4, and you'll put a dot about there. Make sure the camera angle is right, because I'm leaning over about here, and there will be your line, right? Everybody knows that method. Well, they would try to mix it up, in Algebra 1, Algebra 2 in high school, and they would give you a little bit more complicated expressions. Maybe they put it in something like this form, where you'd have 3x plus 4y minus 5 equals, 2, and they would get more complicated. Then you'd have to move 5 over, you see, and then if you did that, you would get, 4y equals negative 3x plus 7, and then you would divide by 4, and suddenly it would look similar to this one over here, mx plus b form. But you would also get some occasionally that would look more like this, and it would be x equals, let's say, 3/5 y minus 1. And what they want you to do, of course, they want you to convert it to this, but I'm kind of a contrarian. I like to do things the way other people don't. It's the same thing in speech, right? When you're telling a story and everybody's talking about certain events and certain things going on, you can say those things in the most boring, mundane way that everyone else says them. Or you can choose the scenic route. You can say things differently. You can just try to use words that are not often used to express yourself in ways that nobody else does. That can make your speech more interesting. And at least I find it more interesting. It's more interesting for me, right? And so that's what I kind of do here with the math, right? If you look at this, everybody else is probably going to convert it to something like this and then do it. But I said, why? Why do I have to do that? If this can work for this kind of graph, well, I'm just going to do it with that one. Oh, slope is rise over run. Really? Why can't it be run over rise? Says who? Challenge the conventions. That's one of the first things you can do to be creative. Don't accept the paradigm within which you were told to operate. Start thinking differently. Start questioning the preconceived ideas that you're being fed as you go through school, whether they be math, perhaps, or anything else. Maybe you'll discover something that other people didn't think of yet. So you will go down here, and it's very similar. You've got the same thing, x and y axis. Just get it right, correct? You can't just totally reorient the axis at this time. But you want to get the same answer they're getting. You just don't want to do the same work. That's the idea. So -1 is the y-intercept, right? What? Oh, it's the x-intercept now. We have written it in terms of x. So this is no longer the y-intercept, but the x-intercept. So just go to -1 on the x-axis. And instead of going rise over run, you're going to go run over rise. So then it's going to be 1, 2, 3 to the right, and then you will go up 1, 2, 3, 4, and 5. And there you are, 3 and 5, and you will come right through here. Well, it's actually 2, 5, but it's 3 to the right, 5 up. Now, if you were to convert this expression into the y equals mx plus b and check it, you would get 5x equals 3y minus 5. And then you would move the 5 over here, so you would now have 3y equals 5x plus 5. Wait, what happened? 5x, yeah, we're good. And then divide by 3. Y equals 5/3 x plus 5/3. And if you look, it's looking like it's hitting about 5/3 approximately, and you are going to go up 5 and over 3. It's the exact same line. But they had to do all this extra work, and I didn't have to do that. And I like that. I like coming up with ways that are different than what other people do. And there's so many opportunities to do this, especially in competition math. I'm curious if you ever devised this as well and convinced yourself that this is a valid method on your own. I imagine many, many people did, but if you had the same path that I went on, awesome. Let's go look at an example now from an AMC about where thinking outside of the box, thinking contrarily to what you would normally do, could be beneficial. Let's get a look. So at the end of that last segment, I wanted to say one more thing too. I don't necessarily think that it's laziness exactly that is that mother of invention. More so, it's a dissatisfaction with the current level or the current state of our efficiency in processes. And maybe we would like to have a more efficient process. That's not necessarily lazy, that's saving time. And that can be beneficial because time is the most precious resource that we have. So let's do this problem here. It's when you start to think differently, when you start to question perhaps what you've been told about how to solve a problem, then you'll start to find other ways to solve problems that are perhaps more efficient. And so let's give an example of what that might look like on this problem. Suppose that 4 to the a equals 5, 5 to the b is 6, 6 to the c is 7, 7 to the d is 8. What is a times b times c times d? And the typical approach to this problem is usually going to be said to be maybe use logs, even though AMC 10 does not require logs. Whenever you have a variable in the exponent, it's typically a standard approach would be to use a logarithm. So for instance, you could take, there's a few ways you could approach it. You could say, well, I don't know what I'm doing or how I'm going to achieve this, but maybe I could do a log to get the a out. so what base should I choose? I don't think it matters. Choose whatever you want. I usually use natural log, by the way, when I use a base. If I do natural log of 4 to the a equals natural log of 5, why do I use natural log for these situations where you actually should use log? Well, it's really simple. Natural log is 2 letters and every other log is 3. So again, the laziness, it's more efficient. It's the better choice for all of them. But if you chose to go with log of 4 to the a equals log of 5, and for those of you who don't know, it doesn't actually matter, and you'll get more comfortable with logs over time, you could then pull the a in front, which is exactly why we take the log in the first place, so that we can get the variable out of the exponent. So if we did that, you would have a times log 4 equals log 5, and then you could divide by log 4, and look, I have one of the terms in my product, and you could develop a viable solution path that way. It works great. However, again, even if I know a way works great, I like to find different ways. I like to see it in a different manner. Let's look at another way on here. And I don't even know if this was originally my creation or if I picked it up. It's quite possible that along the way of my journey, I picked it up somewhere else, but I really appreciate the value of the creativity. And it stood out to me so much, whether it was my solution or one I got from somewhere else, that I really wanted to share it with you here. See, we have this kind of notion about variables, right? Let's say that I tell you y equals 4x plus 1. And let's say x is 2. What do we do with this? Well, we know what we do with it. Of course, you replace the x. Why? Because a variable is a placeholder for a number. That's what we've been told, right? So y would equal 4 times 2 plus 1. And that in turn would equal 9. Great. Now, let's see a different problem. Let's say I have z minus 2 equals 3w. Okay, what do you do with this one? Well, what if I told you that we could do something with that? I mean, it's a 2, right? And over here, using the same equal sign, 2 is actually equal to x. And you could replace this 2 with x. Why would you do that? I have no idea. And you don't know until you explore and see what happens. So you see z minus x equals 3w. Maybe this serves a benefit somehow. Maybe we found some other part in the problem where we had difference of squares, z plus x times z minus x, and we could do something further with this. Who knows, right? They can be creative with these processes, but the important thing here is to think of it, usually you replace a variable with the number you're plugging in. Now we're replacing a number with a variable. Kind of different, kind of backwards. But that is exactly what leads to the better solution here, in my opinion. Namely because you don't have to use logs, which were not technically required on the AMC 10. So then, how does it work? Well, look at, this is a 5, and that is a 5. They're both 5s. And if that's a 5, and that's a 5, and this 5 is equal to something, I can put the something into that spot where the 5 is. Just like we put x into the 2 here. Okay? So we can replace this 5 with 4 to the a. And you will now have 4 to the a to the power of b equals 6. And of course, you know that when you have exponents like this, you're going to just chain them together as a product. 4 to the product ab, or to the exponent ab as a product, is equal to 6. And look, there's another 6. And this 6 is equal to something, and we can put this something into that 6. And you're going to get 4 to the ABC, and then you'll do it again with the 7, and you'll finally get 4 to the power of ABCD is equal to 8. And now you could just think it's more like 4 to a certain power equals 8. And you might think, oh, but don't you have to use logs now? No, you still don't. You can actually just change them into powers of 2. So we're going to call it 2 to the second power. And then that to the, I'm just going to call it x, right? X is going to represent all of A, B, C, D. And this is going to give you equals 2 to the third. And now you can take this exponent to x and this exponent 3, and they must be equal because their bases are equal, and that's an equal sign. So we get 2x equals 3 and x equals 3 over 2. The same thing you would get with the logarithms, but again, they don't mandate that you know logarithms for the AMC 10, or at least they don't up to this point in time. And so I kind of like this because it's going against the normal way of thought, right? The normal way of thought, if you knew about logs, would be to do something along the lines of what I just said. But to replace the number with the variable expression 4 to the a, kind of different, kind of interesting. That's what they like to do on the test a lot. They like to try to move the test taker into a place of discomfort where your normal strategy might not be the most efficient. But those who can be creative, those who can think about it in a different way, might find a really slick solution and find themselves farther in the test by the end than you will find yourself, which is why you want to develop this kind of thinking. Don't just do things in formulaic approaches, right? Try to expand. Now, let's look at another one. Maybe in this video I will do, I'm not sure, an AIME question where I'll try to talk you through the out loud, the mental calculation that you could do if you didn't have a pen nearby. And we'll show that in just a moment. Okay, so now I want to demonstrate one of the ways that I think laziness, if you indulge your human aspect of being lazy, you would like to relax a little bit. If you were to indulge that, it actually can contribute to speed in your processing. How to go faster when you're solving problems, because when you solve something mentally, right? Because you don't want to get up, you don't want to get a piece of paper, you don't want to write anything down. You just want to see if you could solve it without having to show work or do anything on paper or anything like that. And when you force yourself to do that, you have to find the most efficient way to do it. If you cannot find the most efficient way, or pretty close to it, a very high efficiency method, you're not going to be able to get it because it's too hard to hold all of these things in your mind. And so let's kind of see what that looks like. What I want you to do is challenge yourself. If there's things going on around you right now, other noises and sounds, please eliminate them. You know, don't turn off your TV, other things going on like that, whatever's in the background. And try to focus on what I'm saying and try to actually walk through this mental solve process yourself. If you succeed and you felt like I understood exactly what you did, it made sense as you explained it, please leave a comment and let me know. I'd like to know if this kind of solve process is benefiting more than me just talking and people are lost, all right? So let me know if you were lost or if you were able to follow along. If you do get lost, try to go back to like the 15 seconds prior and re-listen to that part and see if you can get it that way. But let's see what this would look like. I actually solved this mentally when I was with a student in one of my sessions and they were preparing for the AIME and we were going over problems from recent AIME tests. And so we did this one, problem 1, and I was just like, I wonder if I can do it in my head. Let's see what we can do here. So first, there's a lot of repeating things when you're solving mentally, by the way. You have to keep it because your short-term memory is constantly trying to throw that away. I don't need that. Yes, I do. Give it back. You have to keep saying those things if you're going to do it this way. Let S be the number of ordered pairs of integers, a comma b, with a between 1 and 100 inclusive. Notice I don't say 1 less than or equal to a. You're not reading left to right. Understand the concept. A is between these two numbers inclusive. It's an integer. Again, repeating all the ideas as you go. So, and b greater than or equal to 0, such that the polynomial x squared plus ax plus b, we have a monic polynomial. There's a 1 in front of the leading coefficient. And our term here is a, which would normally be where we would see a b. I am going to write this just so you know what I'm talking about. Usually we see it as ax squared plus bx plus c, where b is on the linear term, the term with x to the first power. Now they've put a there, and so we'll have to think about that as well. And it's kind of interesting that there's a 1 here. Maybe we can capitalize on that, right? So let S be the number of ordered pairs of that with these restrictions such that the polynomial can be factored into the product of two not necessarily distinct linear factors. So x minus 2 squared would be fine or something like that, okay? So linear quantity squared, right? Linear factors meaning they're going to be of the form like normally you'd see it as ax plus b, like that. That's linear, right? Like you would y equals mx plus b, same thing, okay? So linear factors with integer coefficients, okay? find the remainder when s is divided by 1,000. The b counts as a coefficient, not just the a because it's in front of the variable. In fact, you could say b is in front of x to the 0 power, no problem, because 0 power is 1. So a and b, both coefficients there. Find the remainder. You probably don't know. I stuttered really bad as a kid. It's actually gotten way better, and so yeah. Find the remainder when s is divided by 1,000. Okay, so what are we doing here? Basically, find the total number, right? And then after you're done, worry about the remainder part. What are they? They're pairs of integers, so we don't have, square roots or fractions or anything like that. And they are not the roots, a and b. They are going to be coefficients of this polynomial, okay? But let's think about it, because whenever I think about polynomials and there's roots involved, if I'm going to factor linear factors with integer coefficients, it means my roots are also going to be integers, okay? So since they're going to be integers, well, we wouldn't. Why is that true? Actually, I'm not gonna. Our problem doesn't really have this. It's more like this. So that's really what we have, right? Sorry, I said I'd do it all mentally, but I need you to at least understand this part where I'm going with that. Because if it was ax plus b, it wouldn't have to be a root integer, okay? So because this is a 1 in front, we know it's x plus something times x plus something or x minus something, whatever else. At this point, we don't know that, haven't determined it yet. So because we're going to have things like this, they're going to be integers. Our roots are, and also in effect will be a and b will be integers, and they're both positive or non-negative, at least in the case of b. So my initial thought was I kind of like when b is 0. And maybe I could try and play around with letting b be 0 and then a being the minimum value of 1, and just think about it, right? So x squared plus x, that's it. Does that have integer roots? I mean, I didn't violate anything, and it's going to create linear factors. It'd be x times x plus 1. The roots are negative 1 and 0. That's okay. It doesn't say the roots can't be negative. So this seems okay. Maybe I should increase b by 1. It's at this point my spider sense kind of tingles, and I go, it's not like my spider sense, I guess, but like, yeah, I don't know if you want to do that. Why? Why would I not want to focus on b? Because b is unbounded in the restrictions. We can go as high as we want, but a has limited values that it can be. It's got restrictions on both ends. So because of that, it's probably the better point of attack. Again, when you're solving mentally, you have to think about these kinds of things. On paper, feel free to explore it. But in our mind, maybe we want to focus on the one that has boundaries. Okay? So if we go, okay, well, we just let a be 1, could b have been anything else if I did that? Well, x squared plus x plus 1, let's say. That wouldn't work. What would the product of my roots be? Because we're going to use Vieta's, of course. You didn't think we're not going to use Vieta's, right? So Vieta's formula says that the product of the roots is this coefficient over the leading coefficient. And since this is a b, it would just be b. That is the product of the roots. Now, since b is greater than or equal to 0, we know that our roots are either 1 is 0 and 1 is not, or they are both positive or both negative. Okay, let's think about that thought. If both of my roots are positive, the sum of the roots, let's say the roots are 3 and 4. The sum of the roots is 7, but that would mean this value is negative 7, because the sum of the roots in quadratics is the negative second coefficient over leading coefficient. Don't just memorize it as negative b over a. Understand those are placeholders and think of it as the placeholder instead. It's the negative second over the first, which would mean my a would have to be negative if both of my roots were positive, and a is not allowed to be negative. So we know our roots are always going to be either two negatives or 0 and a negative. Why not 0 and a positive? Again, second guess yourself. If you did 0 plus 3, your sum of your roots would still be positive, forcing a to still be negative. So that's not allowed either. Okay? So we've got that. We know we have two negative roots. A negative times a negative makes a positive. Again, reinforcing the ideas that you're holding in your mind. And we're not going to focus here. We'd rather focus on the a value. So this is where I started to attack it then. We just let a be 1. If b goes higher, we're going to have an issue because I need the sum of my roots to be -1, how could I do that if b is anything other than 0? The only sum of integer roots that uses either no non-positive roots, rather, the only sum of non-positive roots that's equal to -1, thereby allowing a to be 1, would be 0 and -1. That's it. Nothing else. If you have two -1s, it's not going to add to -1 anymore. It's going to add to -2, and that's a problem. So, okay, it looks like when a is 1, b could only be 0. Oh, what if b is always 0 or something? Probably not, but just, these thoughts occur to you, right? Let's increase a. Again, we're focused on a now. We switched our focus. Because you have to, because this is unbounded, it's going to be more difficult to reason with. You can try it that way, and I bet you could actually succeed doing it mentally, but I feel like it would not be as efficient. Okay? So let's go to the a over here, and now let's increase it to 2. So when a was 1, we got one solution. Again, constantly keeping the short-term memory, latching those ideas, repeating them again and again and again so you don't lose them. When a goes to 2, okay, a is 2, think about it, x squared plus 2x. Well, we know x squared plus 2x plus 1 because that's x plus 1 quantity squared. We recognize that. You're taking the AIME. You know the factoring patterns, right? And distributive property for perfect square trinomials. So x squared plus 2x plus 1 definitely works. Are there any other values that work? That would be when my roots are -1 and -1. Well, I just need a sum of roots to be -2. So couldn't I use -2 and 0? Yeah, that would be fine. That would mean b is 0. So when a is 2, b can take on the value of either 1, the perfect square trinomial, or 0. So that's two values that work for b. But nothing else could work because no other sum makes -2. -2 and 0, -1 and -1. That's it. Furthermore, I don't like thinking about negatives. What if instead of thinking of the sum of the roots, I thought of the sum of two positive numbers that would go kind of right here? Because if I think of those, now I'm thinking about positive numbers, and I like that. Now instead of thinking about -2 and 0 and -1 and -1, I got to keep saying negative, and that's kind of a negative experience, to be honest. So I'd rather not. Let's focus on the factors now. Again, we are updating our approach as we go. Now we're thinking about these two values in the factors. Okay, they could be 2 and 0 or 1 and 1. Look, positives. That makes us happy. Okay, so now what? Well, we've got two solutions when a is 2. We have one solution when a is 1. Right? When a is 1, we have b is 0. When a is 2, we have 2, 0 and 2, 1. Both work and nothing else works. Maybe it's just going to increase 1 to 100. I don't know. Probably not, but maybe. You should start latching on to potential patterns as you go. You're looking for a pattern so you can break the problem down. Okay, quicker, right? Let's go up to a is 3. So far we've got one solution, two solutions, constantly repeating the ideas. If a goes up to 3, I need the sum of my factor pieces to be 3. I could do 3 and 0, 2 and 1, 1 and 2. Oh, wait. 1 and 2 and 2 and 1, those are the same thing. That's going to give the same value for b. Since b is the product of the roots, whether I do 1 and 2 or 2 and 1, I'm going to be multiplying my factors, right? Like right here, those last values, the constants, the L and FOIL, if you will, which is terrible, by the way. You should never use FOIL. It's just distributive property. FOIL doesn't really exist. Okay, it's just used for reasons. Okay, so back to where we were. 2 and 1 and 3 and 0 are the only solutions when a is 3. So now our solutions go 1, 2, 2. So when a is 1, one solution. When a is 2, two solutions. When a is 3, two solutions. 3, 0, 2, 1. I can't go to 1, 2. I can't go to 0, 3. They're the same. You kind of verify these things by repeating them. Second guessing yourself and checking like we just did. So let's go up to a is 4. We still don't quite know how to attack this yet, and we're trying to hold these values. It's going to get painful really quick. We need to find a break soon. Let's see if we can find it. If a is 4, that means the sum of these values here, the back values in my product of factors, right, that needs to be 4. I could do 4 and 0, product of which would give me 0. I could do 3 and 1, product of which would give me 3. And I could do 2 and 2, which would give me 4 as a product here. So if I did 2 and 2, my B value takes on values of 4, 3, and 0. 4 and 0, 0. Kind of weird, we're getting different values for B, but it looks like we're still getting 3 solutions. Again, focus really quickly. We're on a factor with a 4 as a constant and another factor with 0 as a constant. That's good. 3 and 1, that's good. 2 and 2, that's good. I can't go down to 1 and 3 because it's the same as 3 and 1. So regardless of what B is going to come out to be, notice that B isn't even going in a nice way. It went from 0 to 3 to 4. Where's 1 and 2? They don't work. They don't work when A is 4. This also shows the benefit of using A rather than B. Okay, but still, you might want to try it the other way. Don't trust me. Try it yourself on your own. See if you can get a mental solve that way. Let me know in the comments. Okay, so now we're on A is 4. We notice there's 3 solutions. So let's look at the solution pattern now. 1, 2, 2, 3. Is the next one going to be a 3? Is it going to be 3 threes? Also, something stood out to me with the 4. Did you catch it? When A was 4, we're getting this perfect square trinomial possibility. When A is 3, we did not. When A was 1, we did not. Well, that would make sense because a perfect square trinomial is twice the product 2AB, right? If you do A plus B squared, it's A squared plus 2AB plus B squared. You need it to be even. So it makes sense that when A takes on an even value, we can get perfect square trinomials with integers. So maybe because evens produce a different situation where we get this equilibrium value of 2 and 2 and 1 and 1, maybe we should focus on when A is odd versus when it is even. That is a huge break in the problem. There's a nice shortcut coming up too in the calculation I'll show you as well. So A is 2. We got what for solutions? 2. A is 4. We got what for solutions? 3. Is it just going to march? If A is 6, will I get 4 solutions? Let's check. I need the sum of the sum of these pieces, the constant values in the linear expressions. I need the sum to be 6. They could be 6 and 0. They could be 5 and 1. They could be 4 and 2. They could be 3 and 3. So everything from 3 as a smallest value or a highest value to 6 as a highest value. So 6 down to 3, 6 minus 3 plus 1 is 4. And we can see that when A takes on an even value, it's increasing by 1 each time. So you had 2 solutions, then 3 solutions, now 4 solutions. Go ahead and check 8. 8 and 0, 7 and 1, 6 and 2, 5 and 3, 4 and 4. That's 5 solutions. Okay. Seems pretty clear that when A takes on one of its even values, we are going to march forward, adding by 1 in an arithmetic sequence for the total number of solutions. So it's 2 plus 3 plus 4 plus 5. When will it end? Well, how many evens are there? Back to our parameter, there is 50 evens and 50 odds. And so we start from 2 and we get 2 solutions, and we're going to go forward by 1, which means we're going to have from 2 to 51 inclusive. Not fun, but maybe we could modify it. Let's hold on to that. Don't forget, it's 2 to 51 inclusive when A takes on an even value. Okay, let's go back to our odd solutions. When A was 1, we had 1 solution. When A was 3, we had 3 with 0 and 2 with 1. We had 2 solutions. Is it going to do the same thing? Logically, yes. It's going to go 1 and 2 and 3, but let's kind of get a little bit more comfort because we are kind of making a little bit of a guess there. Let's think about why that would be the case. Let's go ahead and check out when A is 5. You would be able to have, again, we're not thinking about the roots anymore. We're thinking about the constants on the back end. They could be 5 and 0. They could be 4 and 1. They could be 3 and 2. Okay? So 5 and 0, 4 and 1, 3 and 2, that's 3 solutions. We are marching forward, adding by 1 each time. We don't get the equilibrium value because there is no 2.5 and 2.5. So if we do 7, we'll get 7 and 0. We cannot go down to 3. You cannot go below the halfway point. So you're going to have 4, 5, 6, 7. You're going to have 4 solutions. It's marching forward, 1 to 50. So we've got 1 to 50 when we do the odds. Basically when the last odd is 99. And you can just check it. Go ahead and check the last one just to be sure, right? So can you go to 49 and 50? No, because you've already would have done 50 and 49, meaning the constant values 50 and constant value 49 add to 99. Okay, that's equal to the A in our problem. Okay, it's not the sum of the roots anymore, it's the sum of the constants at the end. Okay, kind of similar, but not quite the same. We modified it to make our lives easier so we don't have to think about negatives. So you would go from 99 as a top value down to 50 as a top value, and you're at 50 and 49. You would not switch it because then you would have the same ones now and repeat. So how many numbers are there from 50 to 99 inclusive? 99 minus 50 plus 1, there's 50 values. And we started at 1 and we ended at 50 and we added 1. It's the sum of the numbers from 1 to 50. So now let's see. The answer to this problem, if you're following, I hope you are, is the sum of the numbers from 1 to 50 plus the sum of the numbers from 2 to 51. Gosh, that 2 to 51, I really wish it was 1 to 50. Guess what? It can be. Take that 51, 50 what? What? 1, 51, and take that 1 and just put it right in front, right? So we've got 2, 3, 4, 51, cut off the 1, put it in front. Now you've got 1 to 50 with an extra 50. So you're going to have 50 more at the end. Because you had 2 to 51, you already had a 50 in there. But don't forget the 51, we cut the 1 off, there's still a 50 there. So I'm going to have two sums of 1 to 50, and then you're going to have 50 more. The extra 50 that came from the 51 that we split at 50 plus 1 and put the 1 in front. So if I have sums from 1 to n, how do you sum those? You should know this by now. It's the average of the first and last times the number of terms, but you should also simply remember this one because it comes up so often. The sum of the numbers from 1 to n is n times n plus 1 over 2. And always second guess yourself, what's the n times n minus 1 over 2? That's going to be n choose 2. We don't need that. We're not doing combinations right now. Okay? So I've got 50 times 51 over 2, but I've got two of those. Right? So you've got 50, 51, fraction 2, but times 2. Those 2's cancel. What do you have now? You have 51 times 50 plus another 50. If you have 51 50s and you add another 50, you now have 52 50s. So 52 50s, why don't I split 52 in half? 52 in half would be 26 and 2, and I can take that 2 and put it with the 50. Why would we do that? You already know. So we can have 100. And 2600 is not quite the answer. We now have to modify it. It is S. We want the remainder when 2600 is divided by 1000, and that remainder is the answer 600. Did you follow? Let me know in the comments. I'd love to hear if you were able to kind of follow that explanation. I know it's probably a little bit longer we would use when we use the board, but think about if you used your paper now to do that same problem, how smooth and quick the solution would be. Why? Because you forced yourself to find a mental solution. Then on the real test, when you're not solving mentally, you're going to spot opportunities. Like rather than add 2 to 51, you're going to move the 1 in front. 1 to 50 plus 50. And you're going to see that you have two of these. You're going to notice that stuff on your paper. So now you get to combine the efficiency of paper with your brain spotting ways to save time, further incentivizing the efficiency. So that's all I've got. This was my explanation of how laziness, right, can help you on the test. But you need to channel the laziness in a productive manner. We're not talking about, I just lay there in bed, I don't want to do anything, I'm going to be intellectually lazy. We don't mean that. We just mean that maybe you want to relax a little. You worked a lot that day. You did a lot of work. You're on spring break right now when this video comes out, and you would just like to not pick up your pen and not write math on the paper. Why don't you go do some old AMC 8s mentally and see as many as you can do entirely in your head, writing only the answer down. See if you can do them and how you do. Shoot, we just did an AIME 1. Go practice some other AIME 1s. See what you can do. You might be surprised at how your speed and efficiency on the AMC increases because you tried this kind of an exercise. Hope you enjoyed the video. You have a good one.